Last week, I told you about correlation, and I stressed that correlation is about relationships between variables. So for instance, we took one variable, put it on the x-axis, the other variable went on the y-axis, and then we created a line that went through the middle of the dots. That allowed us to see the direction of the relationship and also the strength of the relationship, how close the dots were to that line. And then I strongly hinted that using that regression line, we were going to be able to also make predictions. And this week, I'm going to pay that off. I'm going to show you how to make predictions. I'm going to talk this week about predicting the future. Now, as I get started with that, I'm going to kind of stick with the relationships a little bit because it really makes a lot more sense to think about predicting with behavior. And the best predictor of future behavior, if you want to know how people are going to behave, best predictor of future behavior is past behavior. You look at how they've behaved in the past. So thinking about relationships, let's say you go on a date with somebody and you go out to a nice restaurant. You expect they're going to be treating you nicely, but here's what you can look for. If they're really nice to you, but they're impolite or mean or rude to the waiter, you're with a mean person. You can expect that same behavior is going to get directed back at you at some point when they don't have as much to gain by being nice to you. And you may think, well, but they've never done that to me. The snake in the grass does not have to have bitten you to still be a snake. People reveal themselves and their character through their behavior. You can watch how they're behaving with others. If you get in a relationship with somebody who was cheating on somebody else to get with you, then don't be surprised if in the future you get cheated on because you are with a cheater. Best predictor of future behavior is past behavior. Now, the same thing is true with variables, except what we're going to do is take what we've learned from the past and use that as we're trying to make predictions. So let's say that I tell you a statistical story in which I have randomly selected one individual from the US population, and all I tell you is that he's a male. How tall is he? I want you to predict his height. Well, how are you going to do that? You know nothing about this individual. You've never even seen this person, and I'm asking you to tell me something. So what you're going to do statistically is you're going to see what is the most likely outcome for this variable. And if we're talking about height, then the most likely outcome and your best predictor is going to be the mean. If you know nothing else, and I say I have one individual selected at random, how tall is he? You are always going to guess the mean, the average. That is your best prediction. Well, we look into this a little further and we find, and I did, that the average male American's height is 177 centimeters or 69.7 inches, which is approximately 5 feet 10 inches tall. No matter who I pick, if I ask you how tall is he, you're always going to guess 5'10", unless I give you more information. Unless I tell you I have selected a guy at random from the US population and he's a basketball player. How tall is he? So what are you going to do in your brain? You're going to think, well, the average is 5'10". Basketball players tend to be taller than the average. You're going to use that additional information to improve your prediction. You're going to guess taller than average. And if I tell you that I have selected a guy at random from the US population and he's a horse jockey, how tall is he? You'll do exactly the same thing. You'll take what you know as a starting point. You're going to do a little math in your head. You know something about horse jockeys. You're going to guess a number lower than average. So in every case, what you're doing is using a starting point, and then you're adding or subtracting additional information to make your prediction even better. That is what linear regression is about. It's making a prediction about an unknown y value, some score on a variable, based upon information from an x variable that is correlated. They are related. If we have two related variables, one of those variables can tell us about the other. How is this done? When you apply for college, it is not uncommon, especially in colleges that are competitive in their entrance. They will want you to take an SAT test or an ACT test. What is that about? It's additional information. What they're trying to determine is how likely are you to succeed in college. Now, they could determine that based on your GPA and things that you're participating in. They'll probably use that information as well. But what the SAT is designed to do is to predict your likelihood of success based upon your performance on this test. We could do the same thing if we were hiring for our company. We want to hire people who are going to be successful. But how do we know if they're going to be successful? We start with measuring everybody who is already working at the company. And we use a series of tests. And what we develop is a profile about the people that work there based upon these tests. And then we're going to identify who are the best performers, who has the highest performance metrics. We now know this all across the scale. We know test scores and we know performance. Now when we hire, we're going to give our new hires that exact same test, and we're going to hire the people who have the profile that is closest to those who are already successful. The idea being that we get additional information that we can use to make a prediction that we couldn't make in the absence of that information. What we really have is a tale of two models. The first model we're going to call our null model. It's H sub 0. It's the model that says the best predictor is the mean. So no matter what question I ask you, the answer is always going to be the mean. Our second model, our H sub 1 model, or alternative model, is I'm going to use additional information to make better predictions. And then I'm going to test those two models to see which one is better. Now that makes sense intuitively, but how do I know which one is better? Well, the answer to which one is better is which one has the least amount of error in its predictions. So let's look at making a prediction with the mean, and then we'll make a prediction using additional information. So here I have a prediction of support for mutiny on the pirate ship based on cases of scurvy on board. What you will notice is that each of these dots has a certain distance from the line. That's my error. The further the dot is from the line, the more error is in this model. So here on the low end, I see a great amount of error. On the high end, the error is sort of more, 2/3 of the way down. But all of these values have some kind of error built in. I could take those errors, square them, because I don't want them to cancel each other out, add them all up, divide by n, I get an average amount of error. That is the sum of squares. Or I could use a different model in which I take what I know about correlation, I create a regression equation using that regression line, and that regression line is going to fit inside of my dots like an average. It runs through the middle of all of the dots. I could use that for prediction. Same thing happens when I look at my errors. There are still under predictions. There are still over predictions. However, when I add them all up, square them, divide by n, I find there is less error in my second model, my model using regression, than there is just predicting with the mean. The second model has the least amount of error. And this is called the method of least squares. Least squares, the least amount of error in the sum of squares. So we can play that game. Let's find out what that means to have the least amount of error. Think about how you make your prediction. If I ask you to predict a height, the first thing you're going to do is take what you already know about how the world works. You're going to start with the mean. That's your starting point. And then you're going to add additional information that I've told you, such as he is a basketball player. And you are going to add that in. Maybe you get really clever and you discover by doing a little bit of research that the average basketball player is 4.5 inches taller than average. So you use that information, you put those together, and you use that to make your prediction. So you say that this guy that I've chosen at random should be 6 feet 2.5 inches tall, adding the mean and my additional information. That's your prediction. Now we measure, this individual, we finally get to meet this guy. We measure him, have him stand against the wall. How tall is he? He is 6 feet 6 inches tall. This means that there is some error in my prediction. And I can measure exactly how much error is in the prediction because I know my prediction and I know the actual value. So in this case, using my regression model, I have an error of about 3.5 inches. Every prediction I make is going to have some error. I can add up those errors, square them, divide by n. I can get an average amount of error. I could even plot my predictions against my errors to see if there's any pattern among those predictions and the errors that I'm making. I'm going to use that error term, which is called a residual. I'm going to use that error term as I make those predictions. So here's how this is going to work. Think about the height. That is a value that you predicted. We're going to call that y hat. That is the capital Y with the caret over the top. Y hat means a predicted value. If I was predicting Z, it would be Z hat, or M would be M hat. Just anything that I'm predicting, if it has a hat on it, that means it's a predicted value. That prediction is based on the mean, or the starting point, which is going to be a constant. We're going to call that our first coefficient, but because it doesn't give us specifically any information, it's going to be B sub 0. The additional information, that's the information I really want to know about. That will be my coefficient B sub 1. What I will do is take that coefficient, whatever it is, it's created by my model, and I'll multiply that by some known value. So later on when I talk about burnout and job satisfaction, if I know that this employee has a burnout score of 30, what do you predict for her job satisfaction? You'd multiply 30 by this B sub 1 coefficient, you'd add it to a known value, this intercept, and then that's going to be your prediction. Of course, that prediction is not always going to be accurate. There's going to be some error built in, and we're going to quantify the amount of error in the model. The best prediction is the one with the least amount of error. The regression line is sometimes called the line of best fit because it is the line that runs through the dots in a way that has the least amount of error. So going back to our example with the pirate ship, we can see the amount of error represented using just the mean. We can see the amount of error represented by using regression. And we can see, yeah, there's a lot less error in our regression model than there is with the mean. What we'll then do is use an ANOVA to compare these two models. We'll measure the null hypothesis model, compare that to the second or the alternative model, and we'll see whether that alternative model, in the amount of predictive ability that it has, is statistically significantly better than our null hypothesis model. So we're going to do some simple linear regression. I'll walk you through this step by step. A correlated variable can be used to create this linear regression equation by creating a straight line. I want to show you the elements of that line. There's a mathematical formula for a line, and you may have learned this back in junior high school or before. Do you remember something like a plus bx or m plus bx? That's the equation for a line. We're using that same idea, because that is the equation for the line, but we're going to change the terminologies just slightly. If you're already familiar with that a plus bx model, it still works. We're not losing anything here. We're simply calling it something slightly different to identify the coefficients. The lowercase coefficients like b in our model, that indicates it's something from a sample. If I use a Greek letter like beta. That would mean that it's the interpretation that we're making for the population. When we look at our A plus BX model, we're going to call A B sub 0. So the first element of our prediction is B sub 0. That is a constant. It is the value of y when x equals 0. It's sometimes called the y-intercept because it's the point where the line crosses the y-axis. So to interpret this, what we would do is select an x value of 0, plug it into our model. What is the value that remains? That would be the point at which this line crosses the y-axis. We will also be able to determine whether that intercept is statistically significant. Maybe we get a non-significant intercept. What does that mean? Is that important? Does our whole model crash if it's not significant? The answer really depends upon whether or not you can have a meaningful 0 with your x-axis. So think about, if we're using IQ as a predictor, is there such thing as having a 0 IQ? You might think you know some people that have that, but in reality, there's no way of having a 0 IQ. Or if we're predicting weight based upon height, is it meaningful to predict a weight for a height of 0? If the thing that we're using as a predictor doesn't have a meaningful 0, then it's not going to have a meaningful intercept. Whether the intercept is significant or non-significant doesn't matter. At that point, we need the intercept for the math, but it's nothing we can interpret. At other times, we will have a predictor that has a meaningful 0 point, and then we could interpret the intercept for that. So it really depends on what we're using for our predictions. When we look at the coefficients in our output, we're going to see the y-intercept, or A value, or B sub 0, as this first value as an unstandardized coefficient. In this case, it would be 235.49. The second element for our prediction is the B sub 1, which would be in the place of the B in our A plus BX idea. This B sub 1 coefficient will work exactly like a correlation coefficient. It tells us the direction and the rate of change for our variables. Just like a correlation, the R value tells us the direction, whether it's positive or negative, and it tells us the strength of the relationship based on how close those values are to 1 or negative 1. This beta coefficient would tell us essentially that same thing. Is indicating direction and rate of change and the steepness of the line. If this coefficient is positive, we have a positive relationship between the variables. To think of positive, you could think of starting at the y-intercept and you're walking along the x-axis. In this first example, you're walking uphill. That's a positive slope. If you start at the y-intercept and begin walking along the x-axis and you're walking downhill, that would be a negative slope. But look what happens when the slope is 0. First of all of your predictions are going to be the same. They're going to be the mean value. Second, that line is horizontal. When there is no relationship between these variables, especially as we're predicting what will happen in a population, that beta of 0 means no relationship. In fact, that is going to be our null hypothesis. When we do hypothesis testing, the null hypothesis is there is no relationship, that this beta sub 1 or B sub 1 equals 0. When we look at the coefficients in our output, the unstandardized coefficient for the predictor, in this example it's burnout, which could be B or B sub 1 or beta sub 1, that value of negative 2.11, that is our B coefficient. Now notice over here we have the standardized coefficient for the first beta value. That is a negative 0.65. And if we were to run a correlation model, we would find that the correlation between our two variables is the same as the standardized coefficient for the regression between those two variables. In this example, they're both a negative 0.65. When we add more predictors, however, a second, a third, a fourth predictor, then we're going to get partial correlations. So this value will change. We'll be identifying how much unique variability is explained by this predictor, not just the overall amount of predictive ability. So we'll look at partial correlation next time when we start talking about multiple regression. So here's how we would form up our linear regression equation. We'll start with A plus BX for our prediction. We will then get the A value from the output. In our example, 235.5, that plugs in for A. The negative 2.11 plugs in for B, giving us a regression equation of y hat equals 235.5 minus, because this B coefficient is negative, minus 2.11 times x. When you have this equation, I could ask you to predict a value, an x value of 40. And what you would do is plug that in, 40 times 2.11, subtract that from 235.5, and that would be your prediction. We haven't talked about this error term in a while, so let's go back to that. The error term, that's the difference between the actual values, let's say the height of the guy that we chose at random, and the values that you predicted using your regression line. You made your prediction, you were off by a little bit. That difference is the error term. Each prediction has an error term, but the model also has overall error, and there are some things that are constant or consistent about the error in our model. That symbol is the error. It's called residual variance. It's the leftover variability that we couldn't ascribe to any predictor. Remember the example that I used of having a pie, and our predictors, they're cutting out a pretty big slice for themselves, but there's always something left over. That's the residual variance. That's the variance that cannot be explained. That error term is a random variable, which should be normally distributed and have a mean of 0. The values of our error term are independent. Those values are not affecting one another. We can't learn anything about our model simply from looking at the residuals. It should just be randomness and error left over in our model. So that error term, that is what we're going to use to evaluate how good our predictions are, because we know that in a good model, the error term is smaller. The less error in our model, the better our predictions are going to be. Every type of test, including simple linear regression, has assumptions in that test. We want to check the assumptions for the data to make sure that they match the assumptions for the test. We think that they will, especially if you're coming to a class like this. You trust that I'm going to give you some nicely cleaned data sets that are going to be beautiful. They're going to work just like I promised. But it's important to verify. So let's make sure that our data match the assumptions for the test. The first one, we have to have 2 scale level variables. The first one is our outcome. That's the thing that we're trying to predict. In our example, we're going to predict job satisfaction. It'll be on the scale level. It's quantitative. It's an outcome. And we're going to use burnout as our predictor variable. It's also scale level. It's also quantitative. When I have these 2 scale level variables, I can use them for correlation, and then I can use them for doing my simple linear regression. I should also point out that I can use categorical variables for prediction. So we'll do that when we get to hierarchical regression. We'll use a categorical variable divided into 2 groups. We use that as one of our predictors. However, to do that, we're going to have to play with the coding a little bit, make sure it's coded in a specific way. That is something we're going to learn about next. So right now we're doing simple linear regression. That's just simply 2 variables that are related or correlated. We can check whether there is a linear relationship between these 2 variables by creating a scatter plot. If we see this line running right through the middle of those dots, and the dots are roughly equally distributed. All along that line, we have a linear relationship between these two variables. If, however, we look at our scatter plot and it looks kind of horseshoe shaped, that's not good at all. That is a non-linear relationship. That curvilinear relationship cannot be modeled by a straight line. And if you try it, what you end up with is that horizontal line, which you remember, the horizontal line, that's the same as no relationship. If we try to fit the curvilinear relationship with a straight line, first of all, we're going to have a lot of error. And second of all, we might have a model that looks like there's no relationship, when in fact there is a profound relationship, but we've missed it because we're using the wrong technique. We have to have a linear relationship between the variables for linear regression to work. Next, we have the independence of observation, which means that each of the data points should be collected without influence from others. This is something that we're going to address during our design for our research. We're going to use proper methodology for random selection or random assignment. We're to make sure that everyone in the population has an equal chance of being selected, and when they are, we would randomly assign them if they were to be into categorical groups. We are measuring, let's say that height example. I can just select people at random and gather their heights, but if I select groups of families with siblings, they're probably going to be a lot more similar than they are different. That would be non-independence. So I want to make sure that I have independence of observations. I'll do that with research design. However, there's another way I can check for that. We're going to run a type of analysis called a Durbin-Watson test. Now, the Durbin-Watson test, or a test of autocorrelation, is going to tell us whether or not we have independence of observations. The Durbin-Watson test runs from 0 to 4. We're looking for values around 2. A Durbin-Watson value around 2 says that we have good observations that are not collinear. They're not related to each other. Get values above 3 or less than 1, and now we have a problem with our data. We're probably going to have to transform those data points in order to use them because there's some problem. Or what we'll end up doing is a different type of analysis. So perhaps the reason why we have autocorrelation on our Durbin-Watson is because we have sequential time measurements. In that case, we would use something like a time series analysis. It's a different type of analysis that's going to give us a much better outcome when we have related or intercorrelated data. The residuals should be normally distributed. And what this means is when we look at a histogram of our residuals, we're going to have a lot of small errors. We've done pretty well with our prediction. So in the middle of that histogram, we see a lot of small errors. Larger errors, either small or negative or positive, there's many fewer of those. So it gives us a nice bell-shaped curve in the histogram for our residuals. If that is the case, then when we look at a QQ plot of our standardized residuals, we'll see that all of the dots are lined up on this 45-degree line. Now, the dots represent the residual errors, and the line represents what those residual errors would look like if they were normally distributed. And because we see all of our dots on the line, we know we have normally distributed residuals. We can also see that with our histogram. But what if our residuals were skewed or kurtotic? What would that look like? Now, the reason this matters is because you can't always get a histogram, but QQ plots are pretty easy to come by in most statistical software. If you look at a QQ plot and you see the line sort of peeling off of the 45-degree line, then you know something is wrong. In this first example, I've created a data set which is highly positively skewed. This is a pretty extreme example, but it's really good for illustration because you can see very clearly what is happening. You'll notice when I look at my QQ plot, my quantile plot, I'm seeing on the low end, the dots are sort of peeling up off of that 45-degree line. I'm also seeing that same pattern here on the upper end. There are fewer dots than expected on the upper end and more than expected on the lower end. Look at the pattern for negative skewness. On the upper end, we have more observations than expected. On the lower end, we have fewer observations than are expected. If you see either of these two patterns with positive or negative skewness, you know there's something up with your data set. Now, what if we had kurtosis? Leptokurtosis is where all of the dots are close together, the lines are close together, and we have very thin tails that have been pulled out. Versus platykurtic, look at how there's a lot more data in the tails. If you can imagine a bell curve over this, a whole lot more in the tails than there are in the middle of my curve. So that gives me an S-shaped curve with my QQ plot. You know, so peeling away here at the top. That means they have really fat tails at the top and also at the lower end of my distribution. With the leptokurtic, however, we see that the dots are peeling away toward the lower side on the low end of my quantiles and away on the top side on the upper end of the quartiles. Many fewer observations than would be expected. Homoscedasticity has to do with the distribution of the errors along this line. So what I have here is a scatter plot of the residuals. All of the dots should be equidistant to my predictive line. This is homoscedasticity. There's a black line, that's my regression line, and then there are these dotted orange lines above and below. Now I just added those dotted orange lines to show you that the dots are staying within that boundary. They're the same sort of variability all along that predictive regression line. However, if I have a model that works in some cases but not in others, I'm getting really good predictions on one part of the scale, but it falls apart on another end of the scale, then it'll look more like one of these funnel shapes. So with the increasing funnel, I'm really good at predicting the values on the 0 to 4, 0 to 5 part of the x-axis. But when I get into the upper values, 8, 9, 10, a lot more variability, a lot more error. So I don't have the homoscedasticity, I have heteroscedasticity, I have difference in its predictive ability. And the same pattern would hold true with the decreasing funnel. I'm not very good at predicting at the low end, but I have much better predictions at the upper end. If I predict well in the middle of the scale and it falls apart on either end, then I get this bow tie shaped or fan shaped distribution of my residuals. Here's another example of using predicted values plotted against residual errors. And in this case, if the assumption of normality has been met and there's homoscedasticity, we're going to see there's just a random pattern. They're just spread on there as if you'd taken, a handful of marbles or chocolate chips and just like drop them on top of pizza. They're just randomly scattered on there. We don't see them clustered in one place or another. And if that's the case, then we have met this assumption as well. Here's how we can check the assumption for outliers. We're going to look at our residual statistics to see if we have any leverage points or influential cases. Look at the standardized residuals. If the minimum and maximum do not exceed -3 and +3, then this assumption has been met. We don't have any residual errors that are so large that they're indicating outliers. Now, I'm using 3 for this example. You'll sometimes see 3.29. These are just choices that are made based on standard deviations. So this is roughly 3 standard deviations or 4 standard deviations for that 3.29. So with that, we can actually do a simple linear regression. We use JASP for this example. We're going to first of all look at a scatter plot, and then we're going to run the regression equation, and then we're going to interpret the regression model. We'll create a regression equation and then use that for prediction. All right. Here's the setup for this research. We have a boss who's interested in predicting job satisfaction from burnout. In our previous example, the same boss was interested in knowing whether there's a relationship between these two variables. Now we're going to try to predict job satisfaction from burnout. The data were collected on 200 mental health professionals or counselors. We have an outcome of job satisfaction. We'll use an overall score for that. And the predictor variable is level of burnout. This is something that's been pretty well established in literature. We know that burnout predicts job satisfaction. So we're going to check that with our data, make sure in fact this does hold up, and we'll use that to create our predictive model. we can use simple linear regression because we have two scale level variables. We're going to use burnout to make the predictions. That's our independent variable. We're going to use job satisfaction as our outcome. Now in this case, two scale variables. If we had three or more, if we had multiple predictors, we could also use regression, but that would be multiple regression. We could use categorical predictors and work those into the model. We could even use categorical outcomes if we were doing logistic regression. But for simple linear regression, we have only the two variables, one input and one output. The assumptions that we'll want to check, we'll look for outliers, so we'll check our case-wise diagnostics, make sure we don't have values greater than 3 or 3.29, whichever we decide is to be our cutoff score. We're going to use our Shapiro-Wilk test to check for normality. That's something we can also get when we run our tests. Linearity is going to be established from the correlation itself. We'll look at our scatter plot. We can use that to determine whether or not there's a linear relationship between these two variables. The null hypothesis for our test will be H sub 0 colon beta 1, that's the correlation in the population, equals 0. Or the slope of our regression line equals 0. The alternative hypothesis would be that beta sub 1 does not equal 0. That instead of that slope being flat, it's tilted sufficiently that we can see the strength and the direction of that relationship. And that would be present in the population. Of course, we don't have access to the population, so we'll be using sample data. Our alpha level, we'll keep set at 0.05 for the tests that we do. Degrees of freedom is n-2, and in our example, we have 200 mental health professionals, so that'd be 198 degrees of freedom. I just want you to see we're not departing too much from our typical 0.05 two-tailed test idea, but this is a little more complex model. There'll be multiple tests that we'll be looking at, and we'll use 0.05 as our reference point for that. So let's get started in doing our analysis. We're going to first do a scatter plot, and for that we're going to need to use correlation. Now I've already told you that correlation and regression are related, and you're going to see that especially when we start in JASP because there is no special drop-down menu for correlation. So what I'd like you to do is, now that you've opened up JASP, among the options for the drop-downs, click on regression, and then under classical you'll find correlation. We want to move the variables of interest from the list of variables into the variables box. We're going to put burnout in first, and then we'll drop in job satisfaction. And then among the options, Pearson's R is set by default. That's what we want. Click on display pairwise. We have report significance, flag significant correlations. And under plots, choose scatter plot. When you do that, you'll see a scatter plot that looks like this. And you know, that's a really nice looking scatter plot. We see a strong linear relationship between these two variables. So now we've established linearity. There's no curvilinear relationship. This is going to be excellent for prediction. This is going to provide us enough additional information that when we drop it into our regression model, we're going to learn something useful. So now we're going to run the actual regression equation. So for that, go to our list of drop-downs, click on regression, and this time we're going to choose linear regression. You can see that we have a space for the dependent variable. That's job satisfaction, so we'll pop that into our dependent variable. And then there's a section called method. It's currently set to enter, and that's the setting that we're going to use. There are some other options. We'll talk about those later, but I wouldn't recommend using those unless you had a very specific reason for doing so. The most common setting is going to be enter. Our predictor is going to go in the covariates box. So the covariates contain any scale level predictors. If we had a categorical predictor, we could drop that into the factor box. But again, we'd want to be sure that we had structured our data in the correct way, they should be coded as 1 and 0 to use as a categorical predictor. That will make it easier to interpret the coefficients once we have our output. Twirl open the options for model, and here you see that tail of two models. Model 0 is nothing. It's just going to predict with the mean. Versus model 1 has our predictor in it. That's burnout. There's no changes to make right here, but I do want to point out that plus sign. If we click on that, we could add another model. And we're going to use that when we get into hierarchical regression, where we can create blocks of models that we can then use to test whether adding certain variables improves the predictive ability of the overall model. Twirl open the settings for statistics. Let's grab a few things here. Under model summary, let's get that Durbin-Watson test that I told you about. Under display, we have model fit and descriptives. Under coefficients, we already have the estimates and confidence intervals at 95%. Under residuals, let's get our residual statistics and the case-wise diagnostics. Now, you'll notice right here it says all. And if you click on all, it shows you all of the case-wise diagnosis by case. This we would use if we were running an analysis where we needed to find a certain variable and its residual statistic, because maybe it's greater than 3 or 3.29. We want to find the individual statistics for each individual prediction. We use that, but as you can see, it creates a huge table, which we really don't need. So let's reset, change our case-wise diagnostics to standardized residuals greater than 3. If we wanted to use 3.29, we could add that here, 3.29. But in our case, we're just going to stick with 3. So we'll use standardized residuals greater than 3. And those are the settings that we need here. Twirl open plots. There's two plots we want to look at. Here's residuals versus predicted, and our QQ plot of standardized residuals. And with that, we can look at the findings and start interpreting our model. We're going to begin with the model summary. So scroll down until you find that. We're predicting job satisfaction, so we see that in the title, model summary, JS. The first model, M sub 0, that's our null hypothesis model. That's the one that only predicts with the mean. And what do we see? That's not a very good predictive model. That's our zeroed out model. When we look at the second model, model 1, now we see a better predictive model. So here's how that would look. First of all, look at the R value. That's a 6.5 or a 0.65. That would be the same as the correlation. You might remember it was a negative 0.65 correlation between these two variables. The R squared value is exactly what it says. Take 0.65 and square it, you get 0.423. Convert that into a percentage. 42.3% of the variability in job satisfaction is explained by burnout. The R squared is our coefficient of determination. We're predicting about 42.3% of the variability in job satisfaction. Now the next question would be, is that a lot? Is that good? Is that statistically significant? And to answer that, we would look at our ANOVA model, which we're going to do in just a moment. Also, we see our Durbin-Watson statistic in this model summary. We can see that statistic is very close to 2. That tells us we do not have autocorrelation. We have independence of observation among our data, and that's exactly what we want to see. So let's answer that question of whether the R squared was significant. Does it predict a significant amount of variability in job satisfaction? For the M1 model, we can see that the degrees of freedom are 1 and 198. The F value is 144, and that's huge. Remember, if it was non-significant, that value would be close to 1. And we see the p-value is less than 0.001. That is a statistically significant finding. This model is significant. It predicts a significant amount of variability in the outcome. Now, because we're only using one predictor and one outcome, we can just interpret at that level, at the level of the whole model. Later, when we do multiple regression, we have multiple predictors, each of which contribute at different levels, or when we do hierarchical regression, where we have blocks that contribute at different levels, we'll interpret our ANOVA for each of those blocks, or each of the predictors. But in this case, all we have is one predictor, one outcome, so it's going to make it really easy. We can just interpret our ANOVA, and we say that yes, burnout is a significant predictor of job satisfaction. To create our regression equation, we're going to get the unstandardized coefficients from our coefficient table. Now, we've already established that M0, model 0, is not as good as our M1 model. So we're going to ignore this top line for M0 and only report the M1 model. We need A and B, or B sub 0, B sub 1. That first coefficient is 235.456. That will plug in for the A section of our A plus BX. Our second coefficient is a negative 2.112. So instead of A plus BX, it'll be A minus 2.11 times X. This second coefficient being negative, now we're subtracting. That's because there's a negative relationship between burnout and job satisfaction. Those are unstandardized coefficients. But we also have standardized coefficients. And you'll notice that negative 0.65 for the standardized coefficient, that's the same as the correlation that we saw when we ran our correlation model. The interpretation of this standardized coefficient is that for every 1 unit of change in X, there's going to be a negative 0.65 unit of change in Y. Now, that may not be very good for real-world interpretation, but it would be excellent when we're making comparisons between models to just look at those standardized coefficients. We can tell directly how much of that change is due to each predictor. So we can compare standardized coefficients in a way that we can't compare unstandardized coefficients. So let me explain that actually a little bit more. With unstandardized coefficients, they are going to be in the same scale as our original measure. If we're using years of education to predict income, we'll be able to interpret that model very, very simply. We might say something like, for each additional year of education, lifetime income increases by $100,000. That's easy to understand, easy to interpret, as opposed to for each 1 standard deviation increase, there is a 0.683 standard deviation increase in income. Hard to interpret. So we will report unstandardized coefficients. They're in the same unit of measurement as the scales. However, if we're going to do comparisons between the models to find out which predictor is predicting how much, then we're going to rely on our standardized predictors. So these are reported in standardized scale-free terms. They will look like z-scores, essentially. And this will allow us to compare between studies. The interpretation is not so easily interpretable. So a 1 unit change in stress leads to a 0.37 unit change in blood pressure. But if we have other predictors, and one of them predicts 0.45 unit change, that's a stronger predictor. And the one that predicts a 0.02, that's a much weaker predictor. We can compare those predictors much, much, much easier using our standardized coefficients. So we'll use unstandardized as we're creating our regression equation, but we'll use our standardized coefficients when we're doing model comparisons. Now that we have this output, we can take these components and we'll create a linear regression equation that we can use to estimate the values that we're going to find in our population. So here's how that would look. The regression equation that I've created is y hat 235.5 minus 2.11x. With that, I can give you an x value and say predict the y value. You would plug in, let's say I give you an x value of 20, you'd plug in 20 for X, you'd multiply that by 2.11, and then subtract it, because it's negative, from 235.5. And that will give you a value of 193.3. For a burnout score of 20, you would predict a job satisfaction score of 193.3. I could use that same technique. Like if I give you a value of 30 for burnout, what do you predict job satisfaction would be? Well, you'd multiply 30 by 2.11, subtract that from 235.5, you would predict job satisfaction at 172.2. And if I gave you 40 as the burnout score, you'd multiply that by 2.11, subtract it from 235.5, you get a value of 151.1. So you see the pattern. As those burnout scores increase, we're seeing a decrease in job satisfaction. It is steadily going down. But there's an important thing to remember when we're making predictions, and that is we should limit ourselves to the scale of the data, the range of the data that we use to create our model. Let me show you what happens if we ignore that. In this example, I'm using age to predict height. But notice that the ages run from 4 years old to 12 years old. This is a pretty good model because little kids grow up. If we're predicting between ages 4 and 12, we're going to see a pretty good linear relationship between those two variables. If, however, I want you to predict how tall will someone be when they are 40 years old, you'll get a value like 12 feet, 8 inches tall, which of course is ridiculous. You're predicting outside of the range. What we know is that there's a growth spurt that occurs until you get into adolescence, and you stabilize, and you're going to stay that same height probably for the rest of your life. It would be like saying, based on the snowfall today in January, we'll have 14 feet of snow on the ground by the 4th of July. Predicting outside of the range. There's additional information that's not being accounted for in the model. So you'll always want to restrict yourself to the range of the X value data. So let me show you how this could work with our example. If I ask you to predict job satisfaction based on a burnout of 25, you'd plug into the model, you get 182. For 50, you'd get a 129.96. For 70, you get 87.76. But if I ask you to predict what will be the job satisfaction score for someone who has a burnout level of 120, you plug that into your model and you find the job satisfaction is a negative 17.74, which is kind of weird. Most scales don't run into the negative values. How is that happening? Well, let's take a look at our X values. If you notice the range of the data on X, it's running from roughly 30 up to 70, a little over 70 values. And we see a nice linear relationship between there, but we're topping out around 70, 72, 74. All right. If I ask you to predict 120, that goes way beyond the range that we have established for our model. So it is not very accurate because you are predicting outside of the range. This is what the APA style write-up might look like. We start off by describing that we did a linear regression between the variables of burnout and job satisfaction. We checked our scatter plot to determine there was a negative linear relationship, and we examined our standardized residuals to determine that there were no outliers. We checked residual errors with Durbin-Watson test for independence of observations, and the residual plot showed homoscedasticity, not heteroscedasticity, and the normality of the residuals. So the first step is we're showing that we checked all of the assumptions. Now we're going to write up the model. We see that burnout statistically significantly predicted job satisfaction, accounts for 42.3% of the variability in job satisfaction, and we could actually use that for creating our regression equation model so that we could predict different levels of job satisfaction using burnout. We have a statistically significant finding here, and we're also reporting the 95% confidence interval and there's our beta value. And the interpretation: for each 1 unit of increase in burnout, job satisfaction decreases by about 1.8 to 2.5 points. Now, we've gone from relationships with correlation to making predictions using regression. But we're only using one variable to make that prediction. So where we're going to go next is using multiple scale level variables in order to make a prediction, and that is called multiple linear regression. And that is what we're going to talk about next time.